started. Welcome. My name's Matt Mason. I'm here to introduce Rod Brooks. And of course, everybody already knows who Rod Brooks is. That's why you're here. Nonetheless, it's part of the ritual. So I made just a few notes. Well, Rod is the founder, the chairman, the former CTO of, the current CTO of Rethink Robotics. Still current, right? The founder and former this and such of iRobot. A professor at MIT, now professor emeritus at MIT. He was the director of the AI lab and CSAIL at MIT. So those are some of the positions that he's held and the things that he's done. Of course, those are really kind of the outward signs. One of the things about Rod is that maybe what first caught a lot of people's attention was his, I'm not sure it's the right word or not, iconoclastic approach to robotics research. He wrote a paper, I think the title alone tells you something about Rod, called Intelligence Without Reason. And a very intriguing paper. I think he wrote a paper called Fast, Cheap, and Out of Control. It got made into a movie. So what is it about Rod? Obviously there's something going on there. iRobot, as you know, is a consumer robotics company. I don't know if you have one or not. I have a Roomba in my house, and it vacuums my rugs. And so that's kind of interesting that we have Rod to thank for vacuuming our houses. It's an interesting stretch between intelligence without reason and vacuuming houses. So now, about 4 years ago, Rod kind of dropped out of view. And this became a big deal, a mystery. People were all asking, what is Rod up to? And he wasn't exactly saying. There were some hints. He had recently been giving talks and interviews about the idea that robots should be easier to install. They should be easier to program. And I remember there was an interview where he said that perhaps somebody that owns a small bakery would be able to order a robot out of a catalog and install it without having to pay for engineers and so forth. So this was a pretty radical idea. But the interesting thing is, I think, that somebody can come from robotics, can think so deeply and with such originality that then create a revolution in industrial robotics. Now, is it a revolution? Does it say revolution here? It says a new class. Revolutions, I guess, get measured in part by the ultimate impact. And at this point, I would say we don't know. At least I don't know. But for the purposes of this event, I think that's irrelevant. What we're seeing is somebody that takes on the problems, thinks about them in a very fresh and original way, thinks about them deeply, and then goes after it in a way which might actually have a huge impact on our lives. So I believe this is the first real technical talk that Rod has given on this subject. It's quite an event for us. I think it's the biggest thing since President Obama came to talk about the National Robotics Initiative. Or maybe bigger. This is the debate, I'm not sure. Anyway, please join me in welcoming Rod Brooks.
Well, thanks very much, Matt. That was very kind, and thank you for wearing a tie, and Mike Erdman wearing a tie. I'm very honored here. I didn't bring one. I am indeed going to talk about this new class of industrial robot, and I agree with you completely. We don't yet know whether this is going to be successful. And it's actually not a technical talk. It's the first public talk about Baxter. This is the first time I've talked in public about this robot, Baxter. On Monday, there'll be some people from Rethink Robotics here to talk to various people about a software development kit, and CMU is the first place we're going to talk to anyone about that. And Monday after next, we're going to show Baxter for the first time in public, and it's going to be in Pittsburgh too. So somehow, this is all Pittsburgh, Pittsburgh, Pittsburgh. Anyway, I'm very honored to be here. Thank you for coming. And so I want to tell you about Baxter. Baxter is an industrial robot. And it's a little different from other industrial robots, and I want to tell you how I came to this, how we came to this, the company Rethink Robotics, and I'll show you some videos of it, show you how people use it, how you can use it as an industrial robot, and some of the things it can do, and where we think it's headed. This is a real factory worker in a real factory, and she had met Baxter not too long before, and had learned how to train it to do tasks in the hour she had known Baxter, and was she sort of liked the robot a lot. So I want to tell you sort of two themes which got me to the problem that we've been trying to solve at Rethink Robotics. We were originally called Heartland Robotics, by the way, but we renamed ourselves to Rethink Robotics. The two themes are human-centric robots and the question of how we manufacture our consumer goods. So I'm going to talk about those two themes for a little bit. Back when Matt and I were young, long before most of you were born, ordinary people couldn't touch computers. They were hidden away behind glass walls. And they were actually hidden away from ordinary people because ordinary people were dangerous to computers, because back then everyone smoked, including Matt. I think he still does, actually. No? Okay, everyone smoked, and the smoke particles would get into the disk drives and cause the disk platters to crash because they weren't sealed drives. So you had to keep people away. But what it meant was, if you were an office worker, the only contact you had with computation was you might get this fan-fold printout with sales reports or something, but you couldn't get access to the information. You couldn't control how the reports were produced. That had to go to this priesthood in the back room, to systems analysts, to programmers, to punch card operators, to computer operators. But then around 1980, things changed, and ordinary people did get to touch computers with the Apple IIe and the PC that came along. And over the next 30-some years, there's been a complete flourishing of computational forms. The amount of computation that everyone interacts with on an everyday basis has totally changed. And it's been an empowerment of ordinary people. Ordinary people get to control information. They get access to it. They're part of the loop. It's not just fed to them. So robots, especially industrial robots, are sort of like those mainframes. They're kept away from ordinary people, this time because the robots are dangerous to the people. And we'll talk about that in a little bit. But what if ordinary people could touch robots? Well, to some extent, they now can. Over the last 10 years or so, there have been a bunch of robots get out there that ordinary people can touch. The top left is the intuitive surgical Da Vinci, and a surgeon touches the robot. Now, you may think as a surgeon an ordinary person, and they may have a different reason. They think it's a different answer than you do. But anyway, ordinary people touch the robot, and then the robot touches ordinary people. And for guys like me and Matt in our age group, if we get prostate cancer, we're going to have a Da Vinci operate on us. That's the standard way to be done in the US now. On the right-hand side there are Kiva Systems robots from a company in Boston, which was recently sold to Amazon, where the robots move the shelves around at fulfillment centers, because robots can easily go in straight lines, pick things up, and bring them back, and the person does the hard task of grabbing out of the bin to pack out the fulfillment. And lots of fulfillment, lots of things that you buy online now come to you through this robot system. In the middle is home cleaning robots. I'll talk about them in a minute. And then a big change in the US military in terms of ground robots over the last 10 years. In fact, in unstructured environments, there's been a tremendous uptake of robots over the last 10 years. Ground robots in the US military, June of 2002, 0, and now over 12,000. Worker robots in people's homes. I said worker robots because I don't want to count the Furby. There were Furbies around before that. But robots that actually do work in people's homes from 0 to more than 8 million, just from iRobot alone. There's other companies that have also produced them. I don't happen to know their numbers. So there's been an uptake of robots in instruction environments, and at iRobot, which we founded back in 1990, we've done a lot of different sorts of home robots, a lot of different sorts of military robots and exploration robots, including sea gliders in the middle there, etc. Why have things taken off over the last 10 years? I think for a number of reasons. Computation has gotten, and sensors have gotten exponentially cheaper for the last 50 years. We know about Moore's law. But sensors have also got cheaper and cheaper. Sensors being driven by non-robotic applications. I don't suppose Hans Moravec is in the audience. Is Hans here? So when I first came to the United States in 1977, I went to Stanford University, and Hans Moravec was there with a robot with a camera on it. And the camera cost $50,000. And he was trying to do stereo vision, so he had to mechanically drive the camera from left to right to get the multiple images because cameras were so expensive. And computation took hours to move it all. But $50,000 for a single camera. A couple of years ago, I saw a camera advertised online, a webcam, for $2.99. I checked, did it include the USB cable? It did, $2.99. I couldn't, I ordered half a dozen of them. I just had to see these things. And why order one and pay the shipping when the shipping was same for $6? $2.99. I got that camera, plugged it in. It was a pathetic webcam. But it was way, way better than that $50,000 camera from 35 years ago. So consumer goods have changed the cost of sensors. And besides cameras, accelerometers, all sorts of GPS, all sorts of stuff has been changed by consumer goods. So it's gotten much cheaper to build robots. Computer vision and SLAM, simultaneous localization and mapping, have made major strides in the last 10 years. That's a technology which has enabled robots to be more effective. And lastly, for certain tasks, robots have passed the usability threshold so that ordinary untrained people can interact with them. You don't have to be a specialist to use the robot for certain classes of tasks. And I learned 2 lessons from the iRobot experience. I learned lots of lessons, but 2 that count for today. The first involved the fact that the Roomba on the right, that was the first Roomba, was not the first home cleaning robot. Electrolux had a €2,000 home cleaning robot out before the Roomba. It weighed about twice as much. It was actually 13 centimeters high, so it didn't fit under the kickboard that you have in your kitchen, that your toes go under. It didn't fit under there, whereas the Roomba was only 9 centimeters high and did. But the important thing was the Roomba was $200 compared to €2,000. Disruptive price point. It went from being a luxury item, and in fact we chose the number $200 first before designing the robot because we realized that that was the threshold at which a person could spend money without checking in with their spouse whether it was okay. And it's important. No, that was a serious thing because then it became an impulse purchase. So, but a €2,000 robot was not an impulse purchase, and it had to be much more useful at that price. So the first lesson is disruptions can create new markets, because people didn't think, oh, I want a robot vacuum cleaner. If only someone made a robot vacuum cleaner. The market was created by it being disruptive. Second thing I learned is they are not us. Who's they? They are the users. We are the engineers. They are not us. If you're really building a product, you have to remember a bunch of things. And this is very different from building robots in the lab. No one from your company is ever going to see or touch the vast majority of the robots you produce. There's not going to be anyone from the development team to tweak them as they go out the factory door, if you're making thousands of them or millions of them. There's not going to be anyone from the development team to hold the user's hands as they start interacting with the robot. There's not going to be anyone there to explain anything. That's the first thing. Second thing is, the users only care about getting their tasks done. They don't care that it's a cool robot or not. They don't even care whether it's a robot. They want clean floors or something like that. Now, whereas technologists, engineers, oh, but it's a cool robot. Surely you're going to pay a lot for it. Yeah. Real robots have real users. That was the second thing that I learned. Real robots have real users. And so I class PhD students as unreal users. Sorry, but you are not real users. You're special. You're the guys who, the women, men who create the technology. That's not the end user. They're not us. So if you look here at the Roombas as they went from the top right across these later and later models, you may notice that the complexity of interacting with them got simpler and simpler. The first one had a toggle switch on the right for off-on. We got so many telephone calls on the support line. Which way's on, which way's off? That was really hard. What does SML mean? Small, medium, large room. So by the time we get to the bottom there, you can go deeper if you want, but the simple way to use the robot, there's just one button in the middle that says clean. There's no on-off switch. And this is important. You just press the clean button and it goes and does a task. You can specialize a little more by going some deeper with some other smaller buttons, but the simple use is just press the clean button. Now, when you put robots out there, people do weird stuff with them too. On the left are the iRobot Creates, which we meant people to hack. We meant people to do weird stuff with. Other people just hacked them anyway, and they did variously interesting things or not. But they also used them sometimes in strange ways we didn't anticipate, and they didn't realize they were using them in strange ways. So one of the things we had was a virtual wall, still have the virtual walls, where if you want a robot not to, suppose you want it to clean this floor and you don't want it to go out that door over there, you put a virtual wall, an infrared beam, you just put it down, crossing the boundary there, and the robot won't go out, wander off down that way. So you can sort of partition off parts of your house to keep the robot contained. So we then, one of our people was in Denmark and heard that at a elderly care facility, a government elderly care facility, all the floor cleaning was done by Roombas. Well, this sounds interesting. Let's go see how they do this. And he went and he saw the woman in charge of cleaning. She was very happy with her Roombas. She loved the Roombas. And he just wanted to, see how she used them. So he asked to watch as she used the Roombas. So the first thing she did was she got a virtual wall, she turned it on, pressed the clean button, and then put the virtual wall on top of the robot. And she had multiple ones of them. And what this actually did, and she had no idea, she thought that's how you were supposed to use them because she hadn't read the instructions. Now, I don't know if people know the Bratenberg Vehicles, that book from 1984 about simple robots. She'd built Bratenberg vehicles out of these things so they'd stay away from each other and they'd sort of spread out and clean the floor. But that was purely accidental. We also had a lot of robots in Iraq and Afghanistan dealing with improvised explosive devices. And they're real users. They're 19-year-old kids out there, soldiers, US soldiers, bullets flying past their heads, using these robots. But up until in the early 2000s, the youngest kid in the squad had to put on a bomb suit, rope around their belly, they'd go out with a stick and poke things, which ended badly often. Now, a robot has to be sent out. But there were two major sorts of robots in use in Iraq and Afghanistan, one from iRobot in Massachusetts, another from Foster Miller in Massachusetts. It's sort of surprising how the competitors come from right next to each other, owned by Kinetic now. And we knew our robot was fully digital, had Ethernet. It was a much cooler robot than that stupid Foster Miller robot. It was a good robot. Their robot wasn't very good. But word came back from the field that our user interface, which was really, really good, our user interface sucked, was the word, compared to the Foster Miller one. Well, one of the iRobot engineers said, well, we need smarter users then. Okay. That wasn't the right solution. The right solution was to put a game controller on the robots. 5 minutes of practice without any documentation. The people in the field got to use the robot effectively. They had maybe 85% of the capabilities of the robot. Our engineers, but they don't know how to do these other things. Well, before, with months of training with the complex interface, they never got to 85%. Now they got to 85% in 5 minutes. It's like the clean button. Match something to where the users are in order to make it usable, and you get much more effective use and much better uptake. That was the first theme, user-centric robots. Second theme, I had been going to China since the mid-90s to look at low-cost manufacturing. And first to manufacture robot toys, which we used to make, and then to manufacture Roombas. This is a Roomba factory in China. It's a bunch of people building robots by hand. Very simple infrastructure, very simple tools. They're building stuff by hand. February of this year, ABC Nightline did a report on how iPads are built. And they pointed out that, well, their statistic was 325 pairs of hands touch an iPad during assembly. So, you know, our stuff, the stuff we buy, the consumer stuff we buy, is still made by hand. What year is it again? Still made by hand. You know, lots of things have been done by hand in history, and then they're not done by hand. So, you know, a lot of farming used to be done by hand, and now it's done by tractors, and et cetera. But there's other stuff that used to be done by hand. People here heard of telegrams and the telegraph? Commercial telegrams. There was a person who would read stuff and then use that key that in the right-hand corner to turn from words into a signal and go over the line, and then another person would listen to the signal and transcribe it down and get the telegram out. Does anyone know how long we used telegrams for in this country? They sent messages by hand. We started January of 1838. That's when the first commercial telegram was sent. Anyone guess when the last commercial telegram was sent in the United States? 1979. No, it was January 2006. But good try. Took a damn long time for the internet to kill off those telegrams. Internet's a little faster than telegrams, but eventually it did. So my question is, after 232 years, when will we stop building our stuff by hand, the stuff you buy at Walmart? When will we stop building that by hand and use machines? By the way, US manufacturing productivity has increased faster than other productivity in this country. It's increased very, very, very well. US manufacturing output has increased roughly 3.7% per year with for 60 years, which is a pretty good run of increase in productivity, mostly flat unemployment. It's gone down a little recently. But how's that been done? Well, we have moved to the right-hand side of this. We've gone to higher value-add manufacturing in the US and let lower value-add go offshore. So higher value-add is building jet engines. Lower value-add is building saucepans that you buy at Walmart. In fact, there's a great statistic, you may have seen this, Matt, of the cost of an airplane for the US military and the US defense budget, and they cross in 2054. The whole US defense budget at current projections will buy one airplane. Now, fortunately, the US defense budget's a big number, so manufacturing will still be healthy, but that's obviously not sustainable. So, since World War II, we have outsourced manufacturing to low-cost labor regions. First to Japan in the wake of the Second World War, and then as things got back together there and the standard of living went up, moved to South Korea. As the standard of living went up there, moved to Taiwan, then moved to southern China. By the time I was building toys in China in 1998, 1999, plush, the sewing part, was too expensive to be done in China even then, and that had already migrated down to Vietnam. So, you know, there's this constant move of low-cost labor, and behind it, increase in standard of living, and new consumers come up behind. Well, where do we keep going to? Well, you know, meanwhile, Thailand has had a total industrial revolution in the last 30 years. As manufacturing in Indonesia, Malaysia, you're sort of running out of places to exploit. And in fact, you can see the history of manufacturing in the hourly cost of labor. You can see exactly the march, and these numbers keep coming up. This is from around 2003, 2004, or 2006 up there, 90 cents an hour, the total cost of manufacturing in China. It's now up to about $3. It's increased rapidly, and you've probably seen stories from Foxconn that make the iPad and iPhone, that the wages have gone up dramatically in the last 2 or 3 years there. Because the workers are saying, enough's enough, we need to be paid better for this. So what will it take to break out of making cheap stuff by hand? So, I'm a robot guy. The answer is a robot. Ask me any question. The answer's a robot. I admit it. I wanted to say that, we've sort of got into this thing here in the US where we talk about advanced manufacturing, but I think we make the mistake that advanced manufacturing means manufacturing advanced stuff. You can also use advanced manufacturing for manufacturing low-tech stuff like saucepans, etc. So I gave my punchline of robots 3 slides too early. Sorry about that. It's a brand new talk. It really is. But there's also a bunch of pressures saying that we should manufacture in the US. One is responsive short supply chains. When you manufacture something in China, you have to say 29, 30 weeks ahead of time how many you want of a particular item to appear on a store shelf 29 or 30 weeks later. And by the way, now every retailer wants their own pack out. So the Costco box has to be a different box with a load more stuff in it than the Sears box or the Bed Bath & Beyond box or whatever. So 30 weeks ahead of time, you're not only predicting how many things you're going to sell, but how many you're going to sell them in each retailer. And at iRobot, we were making stuff for linens and things, and they went bankrupt before the stuff arrived. So short supply chains, responsive supply chains, it'd be better if you're manufacturing in the US, so there's not as much delay. If you're innovating and trying to manufacture in China, it's very hard to innovate because the manufacturing is a long way away. Manufacturing, innovating, having manufacturing close, if it's just an hour drive or a 2-hour flight or something, you can innovate much more quickly. Intellectual property. Everyone I know who's manufactured stuff in China has seen copies of their goods appear on other markets. And if you can be more productive, then maybe you can beat cheap labor. And lastly, the only prediction I will make, I won't predict whether our robots will succeed or not. I predict cost of oil is going to go up in the long term. I'm confident of that prediction. And in 2008, when there was a spike in oil prices, most retailers in the US lost their margins completely to oil surcharges. There's all these reasons to bring stuff back to the US, and now my answer, combining these two themes, we'll use robots to do it. Okay, that was what I was trying to get to, but these robots can't be the same sort of industrial robots we have today, the mainframes that are away from ordinary people and ordinary people can't interact with or program. The world's first industrial robot, by the way, was the Unimate, made by a company, Unimation, Universal Automation, first installed in a General Motors factory in New Jersey in 1961. Later, Unimation was bought by a Pittsburgh company, Westinghouse, and then sold off to Kawasaki. But back in 1961, there were a bunch of technology limitations. There was no computer. Computers were too expensive. They used ladder logic. And there were no sensors. So the robot did the same motions repetitively. And industrial robots, to a large extent, still do that. They don't have sensors on them. They don't come with many sensors. You have to get a systems integrator to put other sorts of sensors and software packages. But they're unsafe for people to be around. They're engineered to be precise and repeatable, and what they do well, and they do amazingly well, is follow a trajectory accurately, repeatedly. They'll follow the same trajectory to 0.3 millimeter accuracy for 10 years nonstop. But they haven't been made adaptive or flexible or easy to use. And you have to really structure the environment. You have to clean it up to let them operate. And the integration cost of getting the robot into the factory is 3 to 5, some people say as much as 10 times the capital cost of the robot because of all the other equipment you have to do, the way you have to reorganize your factory. So the industrial robots of today are nothing like what we see in our information technology. The information technology revolution hasn't come to industrial robots. And in fact, there's over 300,000 small manufacturing companies in the US which don't have robots because the cost of entry, the barrier to entry is just too high. They're too hard to use. You need consultants who understand quaternions in order to use them. Now, everyone here at the Robotics Institute understands quaternions, but out there, in the real world, ordinary factory workers don't understand quaternions. Actually, maybe only Mike Erdman understands quaternions, I'm not sure. And so the cost of getting them there, they only make sense for very long production runs. So I decided that we would try to do something about these problems, make it easy for robots to go into factories. I started this company, now called Rethink Robotics, in September of 2008. It's based in Boston, Massachusetts. It's venture-backed. We announced our first product on September 18th, and we're just starting shipping now. I'll talk about supply chain in a minute. And there's the robot with, he's actually a worker in a factory. And you see the logo up there? Notice the orange and the red and the round head and the square head. When we brought the logo out, I thought, Matt, you said we weren't saying what we were doing. I thought when that logo came out, everyone said, oh, they're building humanoid robots. But no one seemed to get it. So that's Baxter. The robot's name is Baxter. It has no gender. It's an it. Baxter is an archaic form of baker, and there were male bakers and female bakers. And we have had two visions. This is going to sound a little bit like advertising, but it'll turn into some technical stuff in a minute. We wanted to change robots so that they could work with people easily, be very low cost. That gets back to disrupting a marketplace. And our idea is not to compete with current industrial robots. It's to go into those 300,000 American companies that don't have industrial robots right now, make it very easy for them to go in there. So we're trying to make it easy to get robots into factories to keep jobs from migrating overseas. This is what Baxter looks like and some of the features of it. It's got a behavior-based. When you buy it for a factory, it comes preloaded with a whole bunch of software. It's not just an empty vessel that you program. In fact, you don't program it at all. You just train it. You show it what you want it to do. And I'll show you how that happens in a minute. It's got two 7-degree of freedom arms, each with force sensing, series elastic actuators. It's got cameras in each wrist. It's got two cameras in the chest, camera in the above the face there. You don't need anything else to train this or program this robot. You just go up and grab its arms, and there's some knobs on the arms and knobs on the side if you want to twist them. And that screen there that has the eyes on it turns into a graphical user interface while you're training it. The arms are compliant. It's safe to be close to the robot. About a 5-pound payload, spec at maximum acceleration, straight out like this for 6,300 hours straight is what we're trying to do. And you can put on different end effectors. I'll talk about that in a minute. It is not actively mobile. There's a base you can get which has casters, and you can push it around somewhere, set it up at a new workstation. And the idea with this robot is that you take it out of the box, you set it up, an ordinary factory worker trains it for some task in 5 or 10 minutes, and then it starts working. When 2 hours later you want it to do something else, you roll it somewhere else and get it to do a new task. So it's a new category of industrial robot. No systems integration. The only interface it needs is a wall socket, a 110-volt wall socket. No programming. You don't program the robot, you train it, and I'll show you some video of that in a minute. And it should be fast so you can change what's done on the line. I was at an event, as was Matt last week, where one of the traditional robot companies said, yeah, we see the need for having lines that get changed after only 4 months. In these small factories that are doing small batches, they need to change their lines in every hour or 2 hours, and so that's what we're trying to do. Wide range of simple tasks. It's aware of its job and its environment. It's not just a machine that's not aware of what's happening. It knows about people, it knows about conveyor belts, it knows about boxes, it knows about certain categories that are in factories, and it adapts to changes. And most importantly, it's such a nice robot, you can be this close to it. You can be right up with it, and it's not scary. I may be scary, but Matt doesn't scare me. So you can be elbow to elbow without safety cages. And it's an extensible platform in that new software will come out and new people will build apps for it, which will increase its capabilities on the basic platform. So just a few technical things about it. It has series elastic actuators at each of its joints. In a series elastic actuator, there's an elastic element somewhere between ground and the load. You can put them in different places. This was an idea developed by Matt Williamson and Gil Pratt. Matt is at Rethink Robotics. Many of you probably know Gil Pratt, who's a program manager at DARPA and funding a lot of robotics work now. You can you measure what's happening on either side of the spring, so you can use that to measure force with Hooke's law. You can control force and stiffness. There's gearbox protection from shock. And so we've got 14 series elastic actuators on the arms. Oh, by the way, by having series elastic actuators, what is the consequence of that? The arms have some natural springiness. With a servo loop, you can change that springiness you can stiffen it up artificially at low frequencies. You have a high frequency servo loop, say 1,000 hertz. You can stiffen it up at a low frequency, but you can't get it as stiff as a big rigid industrial robot. So you don't have precise precision control. There's always some flexibility in the system, but you can vary the compliance. So what that means is this robot is not great at precise tasks, just like actually, Matt is lousy at precise tasks, as we all are. We're really lousy at precision tasks. We use force sensing. We always use force to do alignments and find a cone down which we go in order to get things accurate. Same is true for this robot. So the way you interact with the robot, on the top left there is one of its cuffs. It happens to have a suction gripper on there rather than an electric gripper, but there are two buttons, a round button and a lozenge. And Matt, can you just stand up for a second? Face this way. So, to be a robot. Okay, so the way you train this robot is you come up, you grab the cuff, and the robot's arm immediately goes into gravity compensated zero force mode, so you can move the arm around anywhere. And you touch these buttons here in order to give commands. And then there are buttons here. This face always points this way. And I can twist the knobs and use the graphical user interface, and thank you. And so you see, a screenshot here. This is named this task assemble kit number 2. There's the icons there for putting stuff down, picking stuff up. There's the workspace for the two arms there, and there's various primitive operations. And the robot tries to infer them when it can, or you can go into the menus and give a little more detail if you want. So there's a sequence at the bottom of grabbing the arm at going to zero force gravity compensated mode. And I'm just going to show you a videotape where someone walks up to a robot, makes a mistake first and then corrects themselves, and then programs the robot or trains the robot to do a very simple task in a few seconds. So here comes someone. He grabs the robot. Actually, he made a mistake. He's got to delete, goes back, starts again. Now he's going to train this robot to do a simple pick and place. He puts the arm down and says, suck, and lifts it up. The robot figures out, oh, that must be a pickup. He puts it, he says, let go, don't suck. The robot's now inferred there's a pickup location, a put down location, and so very simple task. It's going to go, pick up, and put down where he said. And there's safety behaviors and error recovery behaviors. I'm going to go into a lot more detail with a better video in a minute to show you in more detail how you do that. So with this very simple programming methodology that you don't need training in order to use, we just let ordinary factory workers play with it, we are able to get the robot to do useful tasks in factories. Here's actually the robot packing its own gears in boxes. By the way, the gears are made in Western Pennsylvania. So this robot is $22,000 for the main robot. There's a little more for the base and the grippers, and it's made in the USA on the right there. That sign. How can you build a? This is about the complexity of a car. How can we build a robot for so inexpensively? Well, a bunch of things, and this is true of anything you want to build in the US. We designed it to be manufacturable. We started looking at every supplier and every technology and made sure our design didn't push it too hard so that it was easy to manufacture. We have a distributed supply chain in 12 states and one province of Canada where modules are built by specialists. So the gears, as I said, are built in Western Pennsylvania. Why would we build the gears in Western Pennsylvania? Because of Penn State University. I'm sorry, it's not CMU, it's Penn State. In their material science, they have really worked on powdered metal. So we build the gears out of powdered metal rather than steel. They have the technology around there. So there are a whole bunch of startups around there that can make those things. So we build them locally around the country where there are specialists. We have testers and calibrators in every place, so we test the modules and the pieces. And then we, and as the case of the powdered metal gears is one example of rethinking the materials we use, just like the Boeing 787 is built out of new sorts of materials and has become much cheaper as a result. So another thing we use is some of the gearboxes have plastic housings to hold the gears in, plastic impregnated with glass, because now that that material technology is precise enough that you can build gearboxes out of them. You wouldn't have necessarily thought to do that in the old days for an industrial robot. And lastly, where we can, we use computation to replace precision. Mechanical stuff doesn't get exponentially cheaper. Computation gets exponentially cheaper. So when you can use computation to have forward models of gear backlash and make predictions of what's going to happen in the gearbox and run that in real time, you can get away with cheaper gears and cheaper components by using computation. You have to have good control theorists to do that. Now, who here has an industrial robot, standard industrial robot? Matt. Actually, no, we'll do this guy. You have a standard industrial?
Oh, I work in that.
Oh, that doesn't count. Well, I'll ask him anyway. He doesn't know the question. How high can your industrial robot jump?
0.
0. Well, yeah, and it's the wrong question, right? It's the wrong question for industrial robot. But recently, Honda announced their Asimo 2, and one of the specs they give is it can jump, I think, 3 millimeters or something. They're very proud of how high it can jump. That's showing its agility. And Mark Rabert at Boston Dynamics, he's got these little hopping robots that can go up 20, 30 feet. So for some robots, how high you can jump is an important metric. It's not for an industrial robot. Okay? So for current industrial robots, the right metrics, which all the manufacturers talk about, are precision, repeatability, and speed. But they're not the right metrics for our robot Baxter. Our metrics are about how adaptable it is, if the world changes, how it can compensate, how flexible it is, how easy it is to use, safety, inexpensiveness, and throughput. Throughput's related to speed, but it's not the actual speed of the moving it. It's throughput, how long it takes to set up the job and get your 10,000 units finished. So different set of metrics. And this is, Matt, you said there's no guarantee that our robot is a revolution, and I absolutely agree. Whether we can convince people that these are important metrics is an unknown question yet, because they are a different set of metrics, and we'll have to see. So we had a philosophy that we should play to the strengths of our robot. It's force controlled, it's not position controlled. That's a different way you have to think about it. But we have error recovery at all levels just built in, and we try to optimize its performance on the expected cases and have it do something elegant when something unexpected occurs, and provide general case robust engineering solutions. Actually, and it's got this built-in intelligence, this behavior-based intelligence that coordinates vision and control algorithms, and out of that comes an elementary common sense. So the robot knows, for instance, that if there's nothing in its hand, it doesn't need to put it down. So if it's going to put something down somewhere and you come and grab something out of its hand, it doesn't then go, as we were talking before, and put its hand in the box to release this thing. It doesn't have it anymore. Likewise, if it knows it's supposed to pick something, if it knows it's supposed to insert something over here, it knows through common sense, well, first I have to acquire it. And if there's nothing here to acquire, I'll just sit here and wait until there's something to acquire. Then I'll put it in there. And that, by the way, leads to the fact that you don't have to teach the robot a task in order. You can just teach the parts, and it puts it together through common sense. Another common sense example. So a lot of traditional robot programming for industrial robots is building in the edge cases, but this robot has a bunch of common sense around it. If I'm programming Matt, I'm going to show him a task. Suppose he's a person. Just for the sake of this, suppose he's a person, and I could show him what to do with each hand, and I say, and by the way, Matt, be really careful you don't let your arms collide with each other. Right? For a person, that's sort of common sense. But if you're programming a robot, you have to make sure that is done. So we put all that in the base level software that's just there. So now let's see how that... and lastly, and I'm going to show some videos. Lastly, the end users can be very different. There are different sorts of end users in factories. And orthogonally to who they are, they have very different styles of using any machine. So the small business owner might be, just tell me the recipe, and the line worker might be a real, gearhead wanting to understand how something works. So there's different sorts of people have different ways of interacting, and I was trying to show you that in the videos. But the important thing that I keep telling my team is, don't outsource hard engineering problems to the end user. Don't say, oh, the user can deal with that. Because the more stuff you lay on the user beyond about one little thing, it starts to be not much fun to use the robot. Okay, so here we're going to train a blind pick and place. So this is not using vision. Here's Noelle. She goes down, she grabs the cuff, goes into zero force mode. She clicks the button that says close the fingers. So the robot just figured out, oh, she meant to pick something up there. So it inferred a pickup location. She released the fingers below, and now she says run. And so it inferred that the pickup location, it's going to do it blind, so there better be something there. We'll come to vision in a minute. It's going to do a pickup. Now it's going to go over to where she trained the put down, but she sort of trained it with a bad kinematic posture, and the other arm was nearby, so it decides to readjust the kinematic posture so that and get that other arm out of the way. There's a force field around it, so it stays away. That force field is used so that the arms can never collide. Okay, so now it's coming down, it's going to pick up another one. Oh, but there's nothing there. So it's going to try again. It realizes try again. It looked a bit puzzled there with its eyes. It glances over where it's about to move. So if you're near it, you know what it's about to do because its eyes tell you what it's about to do. So here we're going to see on the screen the training, new task. It's a little hard to see there, unfortunately washed out, but there's the left plus sign is the position of the left arm, of the right arm. The right plus sign is the position of the left arm. It just inferred that was a pickup. Now she's going to put it down. It says, yeah, I got that. Yeah, that's a put down. And so that's the pick up and put down. And so that was the same task she just trained, but seeing what happened on the screen. She says run, and now it's going to run. Now she's, it's going to put down, feels a force, let's go now. Oh, there must be a surface. I thought the surface was lower, but there's something there, so I'll put down. And it's okay. So the robot is safe to be close to. Next time Matt comes up, I'm going to get Matt to do this. Okay. So the user interface, the slogan we try to keep, two slogans we try to keep for ourselves as we design the user interface is that it knows what you mean and it does what you want. And simple things are simple to train, but you can go into deeper menus if you want to make stuff more complex. So when you do a transfer from one place to another, it's going to assume a default height. But if you want it to be more, you can go in and say, no, I don't want you to go up 22 centimeters. I only want you to go 10 centimeters up from the table. And you can go in and change all those parameters if you must. It'll do something default, which isn't too bad, but you can go in and control it to a deeper level. So here's a task with two arms, and now we'll see some vision training. There are cameras in each hand looking down. But it actually hasn't been told to do anything. It's sitting there, what the hell's going on here? So we'll just see bits of the training here. So she comes in, she brings the, you can see there, it sees that object through its hand and put a circle around that, meaning this looks like an object to me that's different from the background. So you say, yeah, and now it looks around, it's got a rangefinder, looks from different angles, and it's training itself on what the object looks like. You don't have to do anything. It's going to figure it out. You just have to be a little patient sometimes. It looks around. And then eventually it's going to say, yeah, it's confident. You can see the blue ring around it, even with that specular reflection there. And after a while, it's going to get confident that it really knows what it is. It says, yeah, good. I'm ready. Okay. So now, she's also trained it to pick up in some particular area, but pick up those white objects, which are molded plastic objects. So it sees the object, comes in, grabs it off the conveyor, doesn't know the direction the conveyor is going ahead of time. You don't have to tell it that, don't have to tell it the speed. It's going to go and put these in a box in an array for packing over there, comes back, looks for the next object. Now with the other arm, first of all, she's going to put that in its hand. She hasn't trained what it looks like yet. She's saying, what you're going to do with this hand is bring stuff over here, and she can't quite reach, so she goes around the back. Notice the screen keeps following her, so she can see what's on the screen. She gets around there, over here, and she just lets go without it being on the table, so it's just going to do a drop. So it knows it's a drop rather than a put down. Now she's training where to pick it up from. She's training the pick up after she trained the put down. So it says, yeah, that's a pick. And lastly, she's got to go in and say plus I. So she's going to say, yeah, I want you to see this thing that you're going to pick up. So she shows it the rubber ducky, and it says, is that the rubber ducky? She trains the rubber ducky, and now the left hand, which is on the right of the screen, is going to pick up rubber duckies. The right hand, which is on the left of the screen, is going to pick up those white objects. So here comes a rubber ducky below the left hand. It's going to come down, pick up the, oh, it misses. Oh, well, it knows it missed. So it goes and tries again. I can get that. Grabs the rubber ducky and goes and puts it in its swimming pool. And meanwhile, it's going off and putting these objects in this pattern in the box.
Question?
Yeah?
How would you train it to do an inspection task to look for defective rubber duckies?
I'll get back to that because I don't want to miss some action here, but I'll get back to that. So it's doing these two different things with the arms, and off it goes. Then I think then I'm going to show you a little bit more of going deeper into the interface, just to show you that you can specify numbers. First here, whenever you touch it, it thinks it tries to look where it thinks you are, so it's always guessing where you are. She's going to shut it down now, which is the same as pulling out the power plug, and you'll see it just very gently drops its arm. If you pull out the power plug, it does exactly the same thing. So you can be standing underneath it with a power failure. It won't hurt you. That was an important addition that we added. And here, just going into one of these user interface, one of these menus, and she's going deeper. She's going to put a count in there so you can set up numbers, etc. So you can go in and do deeper stuff. There was a question, how would you train it to, where the question, who?
Look for defective rubber duckies.
Oh, it's Chris. Hi, Chris. First off, two things. The first sound's going to sound really wishy-washy, but I know how much you love everything I say, so in your particular case. I said that what we're doing is telling our customers what the robot can do and not expecting it to do more. So since we announced this, all sorts of people have come and been totally disappointed. Like one guy who writes a robot blog came and said, but I thought I'd be able to get it to have it on my yacht and steer the yacht around. How would I train it to steer the yacht? Well, you can't. Sorry. That's answer one. Answer two, I said we're bringing out different versions of software over time. The version that will be the version 1 that's coming out, you can't. The internal versions you can. There's USB ports. You can connect up inspection systems. Another thing in a March, April timeframe will be machine tending, putting stuff into a machine, pressing a button. Those things will come out over time. They're not all there yet. And what that does is it extends into the UI, into the system, and we try to make it infer as much as possible, but you go in deeper into the menus to do more stuff. But you can't do that, you can't do what you just asked until, actually I think January you'll be able to do that one. Yeah. Question?
In an earlier video you showed it packing gears in a box. How do you tell it to go over to the next open space and so on?
Oh, yeah, in fact what you do is, I didn't show that, what you do is you go to a corner and you align it, and then with that number selector, you say it's 5 by 4 array, and then it goes and puts them in there, and it looks to see whether they're empty or not. You train it what empty looks, and if you come up and put a few extras in as it's operating, it will not put multiple ones in there, it will pack the box. So it's really meant that people can do part of the task, and that's the task representation is not a sequence, it's not a program, it's task-based. So if what it senses in the world is different, it will adapt. Now for speed, you might say, don't use vision on this thing. You can switch off vision, just do it blind, but you pay the price in that it won't be able to adapt to changes in the world that can't be sensed without vision. So you, the user, ultimately, if you're a power user, have to make those trade-offs in what you want what sensing you want to have on what steps or not. And we try to make everything default to something sensible so that it works easily. I had said we don't want to outsource hard engineering problems to users. One thing we do outsource, though, is building the hands. So there's a gripper kit. This is the electric gripper kit. This is the pneumatic gripper kit, and I'll just show you how you install a gripper on the robot. So actually, she's going to open up the gripper box, and it doesn't have all the parts in it, but you'll see the parts in a minute. There's different fingers, different finger pads, and there's instructions. We aim at clarity of IKEA instructions. So she's going to put the electric sliders there. By the way, this is a standard interface. We're hoping lots and lots of people will build new hands for this robot. So there's a mechanical, electrical, and software interface. Now she plugs it in, and immediately on the user interface goes from no gripper to I got grippers. Tell me about the fingers. Well, she goes and looks at, she's got a rubber ducky. She just selects the fingers from that pattern and what position she's going to put them in, puts the fingers on, and checks out that this works. And now she puts some finger pads on and makes sure that that grasps well. So she's going to tell it which fingers she used, what fingertips, etc. But if a third party comes along and puts different fingers on, the fingers are visible from the camera, and it's trying to recognize objects, but what do the fingers look like that someone just put on? Well, instead of having to give a CAD model, if you put different fingers on, you can just say train in this thing, and it puts up a different screen. It's got the camera in the hand. It rotates the hand in front of the screen, looks at what it sees with its camera, builds a visual model of the fingers, and now it's able to compensate for seeing those fingers in any image. So there's an example of not asking the user to do something hard, getting the robot to do the hard thing. And here we're just scrolling through different tasks, and if it knows that different fingers are installed in the ones that you trained it with, then it will complain. So things that people using Baxter don't need to know about are a whole bunch of things that used to be in industrial robots that aren't in this industrial robot anymore. That we do have a protective stop. We do have a stop button. When Matt and I were boys, computers had emergency stops on them. I don't know why, but they had big red emergency stop buttons, bigger in footprint than this. It's a good thing we don't still need them, because we'd be carrying around emergency stop buttons. We have an emergency stop button on this robot because industrial regulations say we have to. I have never seen it used in anger, and I hope we never do. It would be a major disaster if we had to use the emergency stop in anger. So there's many things that have traditionally been industrial robots that aren't in this industrial robot. Certainly no fences around it, key switch, etc. We're going to bring out a ROS-based SDK, software development kit, early in the new year. There'll be some people here on campus on Monday just to talk to people and make sure we understand what people here would like in that. Back in the early 80s, there weren't many mobile robots around, and then a few companies started building cheap mobile robots, and out of that came a lot of research on navigation, which led to simultaneous localization and mapping, which led through CMU to autonomous vehicles, which ultimately lead to the Google car, which now everyone knows about. So it was having lots and lots of cheap platforms completely changed autonomous mobile robot research. We're hoping that this relatively cheap platform will change manipulator research, because it won't just be places like CMU that can afford it, but even down to some high schools will be able to afford it, and as they do with mobile robot bases now, and undergraduate teaching on these. So we're really quite eager to get the research SDK out there. And I think lots of people will use this robot for research, some of which will be pretty goofy, but some of which will be pretty exciting. Goofy would be doing the Macarena. I know someone will do it. It's a goofy thing to do with a robot. Sorry. But I expect that people will do stuff with it that's not for did you do the Macarena?
Maybe.
The scary thing was, Sid told me earlier today that his algorithms would be used on every robot in the world.
It's a fact.
Macarena. I guess they're all going to do the Macarena. Okay. But I think people like Sid are going to do some really great things with this robot and some really exciting different things, which won't be in the manufacturing domain. I think that's where the real excitement for me in letting this out to the world is going to be. We've been trying to build a cheap robot for everyone to use. I hope everyone likes it, either uses it in your factories. I know you all have factories, or use it in your research. The robot itself is not a research robot. The robot is a real product, which we're trying to build in very large numbers, made in the USA, and change just a little bit, how manufacturing can be done. So thanks for your attention. Yeah, you have a follow-up, Chris? Do you have a follow-up?
Different question. Philosophical question. Okay, so you're trying to figure out what the user wants, which I think is great. And the intellectual pendulum takes about 30 years to swing back and forth. It looks to me like you're implementing Shankian, I think it was script.
Shankian?
Yes.
Oh man, that's low.
Because, the idea, you go into a restaurant, you know that the first thing you do is you read the menu.
No, they're not. I doubt that anyone at the company has heard of Roger Shank. Although you may just say they're reinventing them, but I don't see them as Shankian. They're not scripts. They're not scripts. There's a bunch of low-level behaviors that run all the time, like don't collide the arms. So if you try and move one arm into another, the force goes up and they can't do it.
Some expectations about ordering. You have to pick something up first. You
Oh.
have to have it in your hand, then you have to put it down. Seems to me like it's the old music is coming back.
I like the Beatles. I really don't agree with you that it's a Shankian script, because a Shankian script is a much more elaborate thing. There's I would agree with you that there's little pieces of knowledge that together combine it, and then you as the trainer, can go in and rearrange things if you don't like the way the defaults come together. But we do try to make the defaults come together in a pretty painless way for simple tasks. So if you really want to charge me with that, I'll plead guilty, but because it works better than the alternative, which is to understand quaternions. Yes?
Have you gone into any factories and looked at the work that some employee is doing and say, yeah, I think the Baxter could do that?
Oh, we've gone into lots of factories, and we've had now hundreds of customers come and look at the robot. There's been we're trying to reinvent a whole bunch of things all at once, and so there's been lots of stuff going on. The VCs, bless the VCs, they always have great advice. You should do this, you should do that, and different VCs demand different things. For a while, some people in the company were really saying, we have to have the robot replace people 100%, and that was not my vision at all. My vision was, you build a tool which has certain capabilities, and in factories, people use it to do part of their task. Like an electric drill doesn't replace a person, it increases their productivity by doing the person lines up where the hole is going to be, and now the electric stuff just does it quickly instead of the person lining up where the hole is going to be and then turning the handle for a long time. So I tend to view it that way. What we're seeing now with customers is with real customers is saying, oh yeah, I can see how I can do this part of this task and that part of that task, and restructure what they're doing in their very simple production line so that they're increasing their productivity. So getting, like in the Kiva system, the robots move the goods around, but they don't do the pick. The person still does the dexterous part. So the customers are partitioning the problem and being inventive in ways to partition the problem. And then they're doing little tiny pieces of engineering of building a fence or something to do an alignment, and so the robot can operate. And so they're doing simple, low capital cost manufacturing engineering with the robot as a component of the task. Yeah, and we've been in quite a lot of factories. We've been in quite a lot of factories. The user interface I showed you is not the user interface we had 4 or 5 months ago. It changed radically once we had a lot of experience with users in factories. And let me give you one example. As engineers, we just got it wrong. As engineers, we thought it was totally natural that you would show the robot how to move an object around, and then that you would show the robot on the screen what the object was by outlining it and saying, this is the object, and then showing, it to the robot. And people say, what the hell do I have to do that for? I can see the damn thing. Why do I have to show that? So that's why we've tried to go that interface there where we just say, learn an object. And it does give you some feedback on what it thinks, so you can say no, and even now, the factory works are still sort of, it's so dumb that you have to teach. What does this teach object mean? So we have had a lot of feedback from a lot of places. Yeah. Yeah.
How does it learn how to handle different types of material, such as glass?
How does it learn? See, how does it know how to steer the yacht? Sorry?
If I wanted to pick up a glass cup, put it in the way, how does it know when to stop?
You mean how much force to apply?
Yes.
Yeah. At the moment, it's just a fairly low force. We've only got a 5-pound object. We're not showing it yet, but an example, we've now got a method which we haven't yet shown, for instance, of how much force to apply to a button. We've got a way of teaching that by moving the arm, and it's a little tricky. So we're developing some methods which will come out later for teaching forces. We haven't got any in the version 1 of the software. The current hand, you can go in, not in the shipped software, you can go in and set a threshold on how hard to grasp. That's not in version 1 software. It will be in a later version of the software. But then there's all sorts of things about glass, for instance. Glass is transparent. It's really hard to do vision on glass. Some things are just hard without a 3D vision sensor, without a 3D sensor. Yeah, I think you're next.
A question about the kind of consumer perception of a robot. So if you have a robot, for example, like the Roomba, that does one thing and one thing only, is advertised in that way, a consumer's perception isn't really going to be that high that they can do other things with it. Whereas this, it's kind of a development platform that you can customize.
Well, there's two things. There's this SDK for researchers, and there's the software for a factory, which are different software loads.
So from a consumer standpoint, though, do you feel like it gets more dangerous for you to bring out a product where the first time a consumer won't be able to do what they want with the robot, it'll be a huge disappointment?
Yeah, that's part of our setting expectations. So we have a national distributor network. We're now getting them to bring in potential customers, and we're doing seminars on. And most of the seminar is about what the robot can't do, which because we're trying to set those expectations for exactly that reason. Because as I said, people imagine that they can do all sorts of things with it, and then they're disappointed. So we really have to damp those down. There was a question back there. Oh, hi.
Foxconn president got a lot of publicity last year for saying he was going to build 1 million robots.
3 million. 3 million.
3 million. And put all his unruly Chinese workers out of business.
He said that on Worker Appreciation Day. No, he did. That was the occasion he said that. That's important to know that.
But if you look at the kind of tasks that they do, building iPads and iPhones, right, it's very precise assembly. It's not the kind of thing that you're doing with your technology.
No, this robot will never build iPads or iPhones. Don't claim it does.
Do you think Foxconn has a chance of pulling off what they claimed they were going to do? Or
Foxconn is trying to reduce the demand for increased salaries. That's what he was doing. I'll eat this if he has 300,000 robots, let alone 3 million. There's nowhere to get them from. He has approached a bunch of companies about it. They can't satisfy him. It's a complex game that's going on there. And it's bad for us because everyone says, why aren't you as good as Foxconn? Has anyone ever seen a Foxconn robot? No. Yeah.
So if you're spending a lot of time managing expectations, why are you not convinced this is too early to bring this out?
Because I'll be dead before it's... I wanted to do it. It may be too early. We may be the Commodore 64 of these sorts of robots. I guarantee 25 years from now, robots like this will be everywhere. But it may be, some company that Manuela goes off and starts after she's seen how we failed so badly. Where's the which one you choose?
Let's just come back to economics for one second. Let's say under the best circumstances, if a task that this machine is ideally suited for, how long does it take to pay for itself?
So the cost of operations is somewhere a little north of total lifetime costs. Lifetime cost is a bit north of $3 an hour of operation of this robot. That's electricity. That's everything. Total cost. So you can work out what that means from that.
But it's a little slower than a human.
It's slower than the human. We have a Tiger team speeding various things up, and it will be, over time it will get faster at lots of subtasks. I never meant it as a replacement for humans. I meant it, when we brought the Roomba out, some people complained that the Roomba took so long to clean the house. They had to sit there for a long time watching it. We really got complaints. I said, don't watch the robot. Go do something else. That's the point. And that's part of the point here. I don't claim that this is a replacement, a plug-compatible replacement for a human. And if it's slower, but it's cheaper enough, then it's okay to do the task that way. And we have, getting back to Matt's earlier point, will this cause a revolution? Depends whether we have got it close enough that enough places in the US find this useful, which then funds us to build the next generation, which maybe does do the Foxconn task. This one will never do the Foxconn task. There's some fundamentally different architectural decisions you have to make to do the Foxconn task. Takeo.
How can user know when he fails to train what he wants to do, that it is his fault or the robot doesn't have that capability? For that matter, are you collecting all the information that users have tried to do and succeeded or failed?
Okay, there's two questions there. How does the user know? And it can be difficult sometimes. So we're trying to put stuff into the UI to help them with that. But there will be cases where if they try to make it steer the yacht and they just can't tell. There will be edge cases like that. So it's about, which is why right now we have a national distributor network of people who go and talk to the customers. Ultimately, we'd like just to sell it on the web with no middle people involved. But it's important for the first few years to have middle people involved who know what it can do to provide some feedback. Are we collecting the data? No, we're not. The robot does have network capabilities, but most of our potential customers do not have network on their factory floor, so we're not adding that as a precondition. We still need to work out a little bit over time under what conditions we are able to get data. I had a great thing on a video that I showed, actually Matt saw at NIST last week at the non-public thing that I had to take off because one of our customers said, you can't show that in public. And it was just some white plastic things that were getting moved around. No markings on them whatsoever, but we don't want anyone to know what we're doing. So there's a lot of sensitivity in these companies about letting data out, and we have not come to any agreement on how that should be handled at this point. And on day one, we won't have network access to them. The way you upgrade your software is you're on a PC on the network, you download a thing onto a thumb drive, shove the thumb drive in, and it auto-updates the software rather than being directly networked. Yeah?
So after the Roombas, it's a little bit of a disappointment to me that Baxter cannot move
So let me tell you another disappointment.
But why not, for example, even if you have virtual walls and you invented all of these, why not imagine that you have kind of a counter and Baxter can be there? So it's not to go around the whole house, but why not imagine that you could put on the counter some kind of like sensor and Baxter could move?
I expect everyone to do things like that, and there's a base here. There's a protocol on what the connection is that's advertised. You can build that mechanism. You can build that base. You can do it yourself. Everyone's disappointed.
But
I
I bought it.
I know.
Day one. I mean,
Thank
I
you.
bought it as soon as there was a click that I could do.
But I just want to tell another story of disappointment. Yesterday, I got email from someone's.
You did the Roombas.
Yesterday, I got an email from someone, an academic. I believe he's actually a graduate of CMU. I was going to check on that. And he said, I can't believe it. You have graphics and buttons. Don't you know that user interfaces of the future are through brainwaves? What is wrong with you people? Okay, we forgot that too.
The analogy from my question to that story is a little bit
No.
upon you.
Okay.
You did the Roombas.
Okay.
Not
Do
me.
you want to know? Do you want to know another reason?
What?
Another reason is there are documents filed with the SEC which released me from my obligations at iRobot on condition I did not build anything with mobility.
Okay, that's like the answer.
Up to a certain threshold, that time has now expired, but it only just expired a couple of months ago.
Let's do one more question. Who's got the best question? Confer among yourselves and figure that out.
The person up there, that one. Yeah, sure.
Yeah. So Baxter is going to be an industrial robot, right? So in industries, there are going to be several people doing the same task. So
Not in these small manufacturers. Not in these small we're not going after the Foxcons. We're going after these small manufacturers where everyone is doing something different.
fine, yeah. So if Baxter is going to replace the people, Baxter is going to do the same task, which several people are going to do the same task.
No.
Are they required? My question is different. So are they required to train all the Baxter?
Oh, okay. Yeah. Once you train a Baxter at the moment, because we're not demanding that work, you just take the thumb drive and you put it in the other Baxter, and it's in the library. Yeah. Sorry, I misunderstood where you're going. Later, when we say that it's okay to put on a network, which we will, but we haven't yet, then it'll just be transferable. But yeah, right now, thumb drives.
Thank you very much.
Thank
It's
you.
been a great talk.